this is just the quick little slide that some of you've already had a preview of where I just test the audio is working. Thank you, Oscar. Great. So hello, my name is Laura Kalbag. And you can get the slides and links to everything that I've discussed today off Noticed at noti.st/laurakalbag/WEPPY3, or you can just scan that QR code there, and I will show it again at the end. So I've been working in tech for around 15 years with a whole variety of teams. I've worked in design, I've worked in development, I've both managed products and I've worked for managers as well. And one of my biggest pet peeves is this separation that we seem to create between our areas of expertise. Like, there's realistically so much overlap in everything that we do, and we do a lot of the time end up doing each other's work, or what would traditionally be each other's work. So a designer makes decisions that impacts engineering. Engineers frequently make design decisions, particularly when there's something that hasn't been designed for properly, like an unexpected state or something like that. And project managers do exactly the same. And we're all constantly passing different documents around each other for feedback and for requirements as well. I mean, sure, there's better ways to communicate with each other, like processes we can employ. We can set our egos aside sometimes, but sometimes we do just need tools to help us get there faster. And because I'm all about uniting all of these different areas of discipline, we're going to talk about managing your application logic. So let's start off with some issues that you might find around state management. So we have complexity. The bigger the app, the harder it is to manage state. Like, even the smallest little feature that you decide to add can introduce a huge amount of complexity around your state. And we have data flow. So passing state between different components can get very complicated and particularly very hard to follow if you've got quite a large code base and you're trying to track the state across all of that code base. We have concurrency. So when different components are interacting with the same state simultaneously, we can get ourselves into some really tricky situations. And testing and debugging, the biggest of things. And the more states you have, it's so much harder to isolate and reproduce those state-specific issues. Like, if you ever use Booleans for your state, you probably know what I mean. You've got a whole list of Booleans just in one file, and it's impossible to debug. So let's be honest, a lot of the time, the sum of our application logic is stored in some engineer's head somewhere, or maybe if you're lucky, multiple engineers' heads at once. And it isn't really easy to communicate the stuff that's stored in your head, especially if you're out of office or you decide to get another job, and then the one engineer who has how everything works in their head is gone. And that can all be very fragile. And maybe you're like me and it could make you lose some sleep at night. So I decided to create a little white noise machine app as an example. And this is because my dog, who was at the beginning, is terrified of fireworks and thunderstorms. And so we found that we could get this cheap little white noise machine off of Amazon, I think, and it just allows him to be calm. And a lot of people, if you've got kids, you might be familiar with it. It's very popular with babies. Just a little machine that makes a white noise. So I think about what kind of states I'm going to have in the design of a white noise machine. Now, please forgive my terrible handwriting here. We've got on, off. There's some classic states. We want to play the audio and we want to pause the audio, because in the web audio API, there is no such thing as stopping audio. You're always just pausing it. We have white noise sounds. So why restrict ourselves to just the noise of white noise? I'm going to add the wave sound. I'm going to add a fan sound. I'm also, because I'm building it for the web, I can have some fun little extras that I don't need to worry about if I was building a practical device. So I'm going to have yellow lights and green lights and blue lights. And of course, volume up and volume down, because even if you are doing something that is on a machine, you often want to control the volume independently of what the operating system is doing. So there's already a really complicated number of different states that will be interacting with each other just for this really basic little app. So what tools am I going to recommend? Well, the clue is in the title. So enter finite state machines. So raise your hand and keep your hand up if you're familiar with state machines already. And put your hand down if you learnt about them because you studied computer science. Yeah, that's pretty normal. Often it's the case that it's something that someone uses when they study and don't really think about much after that fact. So for those who don't know, a finite state machine is a model that can be in only one state at a time. So for example, that is the paused or the playing. And you can change from one state to another in response to an input or an event. And so here we can change on play to go to playing and on pause to return back to paused. So the circles represent the states, and then the arrows, technically they represent the transitions, but they're triggered by the play and pause events. And there's also this really weird little notation that's incredibly useful to know, which is the initial state. So that is that little blob with an arrow that points to the first state, because you want to know when you start your state machine, what state should I start in? So state machines are also a really great visual representation of our code, and we don't tend to get that very often, and it can tell us what our code should be doing. It's not always telling us what our code is doing, but what it should be doing. So I'm going to create a state machine for my white noise app. Before I start to do that, despite my example being quite front-endiness, state machines can be used anywhere in your stack. You're not limited to being front-end, and I will show you a few examples of that later. So I'm going to create my state machine using drag and drop. So my initial state is going to be power off. We start in the off state. And then we can have a toggle power event that transitions us to power on. So far, very simple, very straightforward, finite state machine. Next, we want to have some actions. And so these are our fire and forget side effects, the things that we want to trigger with our machine, and we can implement the functionality later. And it's actually very useful to have that separation of the state machine itself and the functionality that you want to trigger with it. So I don't want to show the buttons on my state machine when it's off, so I'm going to add an entry action. So when it enters the power off state, we hide the buttons. And when we enter the power on state, we're going to have an action to show the buttons. And also, when we exit out of the power on state, I also want to hide the buttons then. So far, more very finite state machine. Now I want to introduce you to state charts. Now this is an extension of state machines that's visual, that allows us to model way more complex logic than we can achieve just with state machines. State charts have been around since the 80s as well, and there's actually a XML, state charts XML, like web standard. So this is all very standards based. So first up, parent and child states. So this gives us the option to add some hierarchy. So inside our power on state, I'm going to add the different sound options that we have. So I wanted to have white noise, and I'm just going to toggle between the different sounds. So I'll toggle to the waves state, and then I will toggle the sound again. So another toggle sound event, and that will transition us to the fan state. And then I'm going to toggle again. It's much easier to code toggles, and that will toggle back to the white noise state. And so that means that whenever you're pressing toggle sound, you go white noise, waves, and fan. And each of our child states also needs their own initial state. So that's why you can see the little circle with the arrow icon alongside that white noise state. And that is saying when we enter into the power on state, we enter into the white noise state as well. So another really useful feature of state charts is the ability to have concurrency. And so these are called parallel states. Mostly states that happen at the same time. So I'm going to get all my sounds, and I'm actually going to make them children of a sound state. So I'm just going to paste them in there. It's a very small screen, so I have to try and optimize what I'm showing, but still make it easy to read as much as possible. I'm also going to add a light state. And I'm going to add a volume state. So that's going to handle our different light options and our different volume options. I'm going to turn this parent state into a parallel state. And so that means that when the power is on, we can be entered into the sound, the light, and the volume states all simultaneously. Next, I'm going to add those actions that I added earlier, but to my sound states. So I'm going to add an entry action for white noise, and it's going to trigger an entry action, which will just change to noise. And then I'll go to my waves state, and I get add an entry action. So when we enter the wave state, we're going to change to waves, and then again, the same for the fan state. And then to my light state, well, earlier I looked at having the different coloured lights, so I'm going to add child states for each of those coloured lights. First off, a light off state, like that's kind of key because we do want to have the option to not always have the light on. And that I'm going to have an entry action to remove the colour that is applied by the other states if we toggle back to light off. So then we're going to toggle the light. This is much like the sound state child situation. I'm going to have yellow, toggle the light. Then blue, and then toggle the light. So on that next toggle light event, I'm going to go to the green state and then all the way back to light off again. So I could just press that button over and over, and I can rotate my way through all of the lights back to the light off state. Can't help but have to make everything neat and tidy because I went to art school. I'm going to add the entry actions. So much like I did with the sounds, I'm going to set the yellow for the yellow state. And I like to make these like really specific names because then it's much easier when I add the implementations later that I can track exactly what they're doing, even if I'm not looking at the state machine itself. And because I like semantic naming. Yeah, you get a bit of an overview of what's going on there. So now I want to show you the concept of self-transitions. And these are actually probably the transitions that you'd use most often in most state machines that you would build. And these are transitions that can fire off and return back to the same state. So you use them to fire off at a particular event and then return back into that same state. It's really useful for doing things like updating context. So I'm going to use this for my volume state. I'm going to add a different event for a self-transition. And I'm going to add volume up. So we're going to hit the volume up event, but we're going to remain in this volume state. And I'm going to do the same with the self-transition to volume down. I position that below the volume state. And so I'm going to add an action on volume up to fire off the command to volume up. And then I'll add an action to volume down to fire off a command to set the volume down. I mean, you could write the code to make this so that the act of the event itself will fire off the transition, but the benefit of encapsulating it in this way means that the state machine is controlling the behavior of your app and not just the events. So next I'm going to add some guards, and that gives us the ability to guard our events with particular conditions. So for example here, if you've got a volume control, you don't want to infinitely be turning up the volume and turning down the volume because there's a ceiling and a floor in how much you can do that. And so I want to create a maximum and a minimum to create some conditional logic. So I'm going to say the volume can only go up, so we can only enter this event and fire it off if is not max volume already. And I'll do the equivalent for volume down as well. So you can only fire off the volume down event if is not the min volume. And that prevents us from getting into those unwanted states and adds that conditional logic. Another concept that works really well with state charts is the actor model. And the actor model is where everything in your system is an actor, and an actor can send and receive events to other actors and change its behavior based upon those events. And it enables us to make our logic a lot more modular and maintainable by breaking it into those actors that are just communicating with each other. So basically, when any one of these state charts is running, it is in itself an actor. So I'm going to make the audio player that actually plays the audio for my white noise machine into its own actor, which means that we can maintain that actor separately from the rest of our code base. And so it's giving us that much more modular thing that's easy to update. And that could be really useful if you wanted to swap out and use a different framework for your audio, whether you decided, oh, I'm just going to use the web audio API, or whether you want to just add some more features just to your audio player in the future. So I don't know, maybe you want to add Bluetooth speakers or something like that. You'll have the option to do that. So I'm going to invoke that actor when we power on. So we want to start the audio as soon as the power goes on. So that's why I'm going to attach it specifically to the power on state. And I'm going to invoke an actor. And I'm going to just call that audio player. And importantly, I actually need to go in and specify that its ID is going to be audio player as well. So I'm just going to, and that will be important because when I enter the power on state, just about to see that, it's pretty dinky. I'm going to use a special send to action, and I'm going to send an action to my audio player actor, and that event is going to be play. So that's saying when you enter power on, send play to the audio player actor. And I'm also then going to add an exit action to pause it. And rather than doing that on power off, I'm actually going to do that when I'm exiting the power on state, because that's when I'm invoking my audio player. Once I leave the power on state, the audio player actor is no longer going to be active because I've left the state that it was invoked in. So having a state chart that is also executable code means you can do really cool stuff like simulating how your machine works. So if I just reorganize this a little bit to make it a bit easier to see on one screen. And then I'm just going to go to simulate. It's a different mode. And so all of the blue blobs here represent the events that can be taken from the current state that you're in. So you can simulate like going into that state, toggling the light, toggling the sound. You can't really see much if you hit volume up and volume down, but you can imagine how it would work. And what this enables me to do is to spot an issue that I have with my state machine. Has anyone spotted what the issue is? I don't actually have an event that transitions me back to power off. So I've only turned it on and there's no way to turn it off. So I'm just going to go back in to my machine and I'm going to create a toggle for the power, just a bog standard event. And I'm going to call that power, toggle off, toggle power. So that allows me to toggle straight back to the power off state. So now if I go back to simulating my machine again, I can toggle power on, toggle the power off, and it works. It's the kind of thing that just being able to visualize your code means that it's easier to spot those missing transitions like that. So I said earlier that state charts can be used anywhere in your stack, and now hopefully you can see the potential of state machines for UI. Here's some back-end workflow state charts. So I asked a guy I was working with to show me some of the ones that he likes the best. So this is just a simple event-based actor. And as I said earlier, a lot of the state machines you'd create are really simple, small things, but they just do that thing really well and prevent you from getting into those unwanted states. So this is an example of a container environment where some of your services, which we might also call actors, they might not be exposed via like a resource URI, and instead they're accessible by submitting an event to the underlying container events manager. Here's a patient onboarding machine where we might want to invoke like 3 microservices, also actors, simultaneously. And this is a serverless workflow. Like maybe you want to integrate with an external microservice to perform a credit check. don't blame me for the credit check example. The guy I asked was American, and so they just think in credit checks, apparently. So through this demo, you might be thinking, well, this is quite easy to understand. Like, I don't have to explain that much, and potentially this is an understandable way of looking at things that is helpful for like so much of the audience. And it's because diagrams are great. There's a visual representation of your code, and that helps with clear communication. So it's really easy to collaborate, and that makes it much easier to spot errors as well, which is really great for documentation. And all of this helps with better planning and organization. And state charts provide all the benefit of diagrams, but they are actually executable code in themselves. And so having your application logic be both visual and executable means that you can essentially use state machines as a living documentation, something that you don't actively have to go and maintain separately from your code base. And that also makes it quite a logical sense of truth, a source of truth, and everybody understands it. It can be kept up to date. Like, you could show a state machine like this to your project manager and they'd be able to work out what was going on, even if they weren't someone that codes. So going back to the problems that we have in software and development, so we have the modular and hierarchical structures in state charts. That helps us handle the complexity that I talked about. The explicitness and the clarity that you're putting into these machines makes that complexity a lot easier to understand. And the visual representation is so great for internal documentation. And we also have a very clear structure for when it comes to testing and debugging, that you could build model-based tests based upon the structure of your state machine. So I'm just going to skip ahead for a moment and add a description and colors to make my machine a lot more useful when I share it with my team. It means I can draw attention to different parts of it. And I've also added a set volume action, because I want to be able to set the volume at a default level when you power on the machine, regardless of what it was at before the machine was powered off. I suppose you could probably set it so that it remembered as well. There is actually a history state, but I'm not going into that today. So to my machine's context, let's look at the context, I've added a volume with a default value of 5, and I've added I'm going to add these XState assign actions. I'll come to what XState is later. And what these do is they allow me to update the context. So they allow me to update the volume when the events are triggered. So I am actually putting a little bit of how, like, the implementation of the code inside the machine, just in this case, because it's something really small and straightforward. So if I go to export all of this as code, you can see that the whole machine is just a JavaScript object, just like lots of nested stuff. And if I scroll right down to the end, so it's actually pretty easy to read like this. I wouldn't say it's the easiest thing to edit like this. It is actually kind of easier to edit it when you're visualizing it. And when we get to the end, you can see where we can add implementation details for our actions, our actors, and our guards. So this JavaScript object is formatted for XState, and XState is a free and open JavaScript and TypeScript library for state machines and state charts. So you can basically use it anywhere that JavaScript runs. So what I'm going to do is I'm going to export that code into StackBlitz so I can set up a little demo app. This actually generates the whole of the demo app code for me. And this allows me to do what I was kind of doing in simulate mode, but I'm just seeing what the current state is, and I'm just using buttons that represent the events to toggle through. So if I jump to a version I made earlier, this is the machine that I had earlier. It's exactly the same as what I showed you. And here you can see that I use the machine.provide method to provide the implementations for the actions that I created in my machine. And I can do the same for my actors and for my guards as well. And if I go to play my machine, this is where we see if the audio is still working. So I power on, and I have white noise. I can toggle through waves, and turn the volume down, turn the volume up again. Can't go any higher than 10. Back to waves. And then if I want to, oh yeah, that goes to fan. And I can turn my light on, and I can go to blue, and I can go back to wave. So this is the concurrency working. I can change the states of the sound and the states of the light. And then I power off, and I've still got green light. So there's definitely something that's gone wrong there. So because I got my logic separate from my implementations, I can just return to my state machine, and I can check out where my issue is. And so this is because I'm only removing color when I enter the light off state and not when I power off. So I'm actually going to add remove color as an exit action on the light state itself. So when I exit the light state, because I'm exiting the child state, I'm exiting when I exit its parent, then it will execute the action as well. So I'm just going to copy that machine back to the machine.js file. So it's a great way of keeping it separate. And now when I run my machine again, nice big flash of white. Power goes on, got my waves working, got my lights working. And if I power off, the light goes off. So that is the wonder of being able to use state machines. So do you always need state machines? Well, no, especially if you have very simple or linear logic. It is an unnecessary complexity on top of that. If you have very small and isolated components, I'd say the actor model might still be useful, but state machines aren't always what you need. When do you need a state machine or state chart? It's kind of the rest of the time. It's so useful for complex systems. It's useful if you want to make it easier to document or to debug or to test. And when you need to be able to communicate your app logic with and share one source of truth with your team. Like, as someone who's worked in both design and development, I find being able to understand what the states are present in an app really useful because it shows me what I need to design for. So you'll no longer end up with missing error messages because your UX writer knows oh, I actually need to write an error message for this, and you're not going to get blamed for having some ugly developer error message thing there. And so everyone gets a better night's sleep with state machines. You can get the slides and the links for all of this from the Noticed, which is noti.st/my name, Laura Kalbag, WEPPY, and also by scanning that QR code takes you to the URL. Thank you very much, and if anyone has any questions, I'd love to chat. You can also be in stunned silence as well, that is also absolutely fine. The tool I use to make the state machines is this, it's called Stately. It's a company I used to work for. I don't work for them anymore, but I still very much believe in the mission, and it's a really useful tool. So I'd recommend that. And it is powered by XState, so it runs, so it works with XState, which also means that your logic is totally portable to somewhere else if you want to use it with something that's not Stately as well. I think it. Oh, fabulous.
Thank you for the presentation. At the end, you said a heuristic for when to do a state machine. You said no simple logic or no small components.
Mm-hmm.
But what happens if the components may be bigger, too big? For example, you said some context, or it's like global variables. For example, what happens if there is some of the actors that set a lot of these context variable? How do you manage to put a limit on the boundary of your state machine?
So you're saying, how do you make sure that if you're componentizing all of your logic out, how do you ensure that they can stay up to date to any changes that are inside of the other actors?
Or even if your state machine becomes too big, where do you put your limit?
Oh yeah, so where's the limit for a big state machine? Yeah, that's a really good question. I would say that componentizing it as early as possible is a good thing. So I'd actually say arguably even that white noise machine, you could probably separate out a lot of those components just to make the code base easier to manage. Because the lights, that's its own component. The sound, that's its own component. And I'd say that where you would naturally want to break things into smaller files or components for the sake of the rest of your code is probably a good opportunity to split it off into a different actor. And that makes it easier to, like, you could have one state machine that conducts like all of your logic and communicates between them, which is like the receptionist pattern. But then you could have everything else encapsulated into smaller actors as well. But yeah, it's kind of, and it depends, but also the sooner the better. It's the same with, I guess, any kind of component-based system. It's always better to do it sooner. Well, I suppose we have an early break then. Thank you very much, everyone. I really appreciate you being here. And you can find me at Laura Kalbag anywhere. I'm easy to find. And I'll be around.